In this video we're going to see how to solve coupled differential equations. So that's where we have two different variables, x and y, where they both depend on time, but they are also dependent on each other. So we can see at the top here we've got the rate of change of the x, which depends on x, but it also depends on y, and possibly some other function of time. And at the same time, the y function, the rate of change of the y function, is also dependent on the x function. So the rate of change of x depends on y, and also the rate of change of y depends on x, hence why we call these coupled differential equations. So an example of this could be predator-prey equations. So for example, we could talk about bears and fish. So if we said that the number of bears is x and the number of fish is y, so that then would mean that the rate of change of bears is proportional to the number of bears that there are, which should make sense because obviously if there's more bears, there's going to be more bears reproducing. So you'd expect the rate of change to be proportional to the number of bears there are. It's also dependent and proportional to the number of fish there are, because obviously the more fish there are, the more food that's available for the bears to eat. And the rate of change of bears could also be affected by some other function, perhaps the climate, for example. Then we'd have the rate of change of the fish, which would be proportional to how many bears there are. So obviously the more bears there are, the less the population of fish would grow, because more fish are being eaten. It's also proportional to the number of fish there are, because the more fish there are, the more the fish would reproduce and the higher this would be. And again, the rate of change of fish could also be proportional to some other function of time, such as the climate or something like that. So that's what this means. The key thing then is, how do we solve this equation to work out a general solution for x, so we could work out how many bears there'd be after so many years, or a general equation for y to work out about the fishes. So this is our process. What you do, let me put these side by side if I can. What we will always do is we will make y the subject of this equation. We will then differentiate that with respect to time so that we are able to get dy by dt. That will then allow us to substitute that dy by dt from here in here, and our y in from here into here. That's then useful because this equation then will only have x's in it, which will then mean that we can solve that differential equation using the techniques we've already learnt before to work out our general solution for x. Once we know that, we can then substitute that in to this equation. So substitute it into here, differentiate it, substitute it into here, and then this equation will only then have y's and some function of t here and here, which we can then rearrange to make y the subject. So that's our process. You could do it the other way around, so instead make x the subject of the dy by dt function, then differentiate it with respect to y to get dx by dt, substitute dx by dt and x into the dx by dt equation, solve it so you get an equation y equals, and then substitute that into the dy by dt function, and then rearrange it all to get x. That's the 5-step process. So let's see what that looks like with an example. So quite a long example here. We're told at the start of 2010 a survey began at a remote island. The number of bears, x, and fish, y, are modelled by these two differential equations. We need to show that d2x by dt squared minus 0.8 dx by dt plus 0.16x equals 0. We then need to find a general solution for the number of bears after t years, and then find a general solution for the number of fish after t years. And then there's a couple of other parts here that we'll come back to in a little while. So let's just focus on part A of the question first of all. So let's follow through those steps that I talked about before. So our first thing we're going to do is we're going to rearrange that first equation to make y the subject. So I've subtracted this 0.3x from the dx by dt. Here. Then to make y the subject, I'm going to times both sides by 10 to get rid of the 0.1. So that gives that. Next step, I'm going to differentiate this with respect to time to get dy by dt. So if I differentiate this with respect to time, then I'll differentiate this with respect to time and get dx by dt, differentiate the x with respect to time and get dx by dt. I can now substitute all of this in here and substitute all of this in here, so that this equation now will only have x's and t's in it. So if I do that, you can see this is here, equals minus 0.1x, minus 0.1x, that's fine, plus 0.5y, so plus 0.5 times this. Next, if I multiply out these brackets and move everything over to the same side, that's just me showing that that's the same thing as that, that's that, that's that. So, like I say, expanding these brackets, moving all of that over to the other side, I get this. And then if I divide through by 10, I get to this, which is what part A of this question asked me to show. Part A there. Next, I'm going to solve this equation. So my auxiliary equation is this, and I find that that has only one solution, which is 0.4. So I can say that my complementary function, my general solution here is a plus bt times e to the 0.4t, which I could, if I wanted to, expand this out to just be like that. Next, I am now going, so this is my general solution for the bears. This is x is the number of bears. So this gives, if I know how, if I can work out the values of a and b, which I'll do in a little while, then I can substitute values of t in, and that'll tell me how many bears there are at that time. So that is the answer to part B of this question, the general solution for the number of bears. Let's work out the general solution for the number of fish after t years. So I need to solve y now. To do this, I can take my x equation I've just found here, and I can substitute that back into that y equals function up here. Because remember, that's what I'm actually trying to find here. I want to know a general solution for y. And given that I know what x equals already, and I can find dx by dt easily, I could just substitute those in and get y. So let's take our x function, which was here or here, and substitute it in. To help me, I'm going to, so this is why it's useful to write it in this form rather than this form, because this form is slightly easier to differentiate. When I differentiate this, I get all of this times 10, minus 3 lots of all of this. So 10 lots of the derivative of this minus 3 lots of this. And then collecting up the like terms, so just multiplying through here, I've got 4a e to the 0.4t minus 3a e to the 0.4t, just gives a e to the 0.4t, and so on, just collecting up these like terms here to give this. So at this point here, I've got my general solution for the bears, I've got my general solution in terms of t for the fish. I now want to use, well actually I've not shown you this part of the question, so let's go to part D. Can I get all of that? not quite. Part D says, at the start of 2010, so remember 2010 was when the survey began, so at the start of 2010, T was 0. There were 5 bears, so X is 5, and 20 fish, so Y is 20. Use this to predict the number of bears on the island in the year 2025. So that means that T equals 15 years after 2010. So basically I want to substitute 15 into my equation, but I can't do that until I know what my constants are, until I know what A and B are. So let's use our boundary conditions then. So I was told that when T is 0, X is 5. So if I substitute T is 0 in here and here, X is 5 here, then I find that A must be 5. I was also told that when T was 0, the number of fish was 20. So if I substitute that into my fish equation, so substituting in 0 here, here, and here, and here as well, gives this, substituting 20 instead of the Y, of course. This can be solved to get B as 1.5. So I know X in terms of T now, because I've worked out A and B. A was 5, B was 1.5. So the question asked me the number of bears after 15 years, so substitute 15 in here and in here, and I find there are 11,094 bears in 2025. Last part of the question. Comment on the suitability of this model. Well, straight away, 11,000 bears seems like quite a lot to me. Let's have a look at our equations, our model. Now, let's look at the bear equation first of all, so I've just got that written here. Now let's consider what would happen to that as T gets bigger and bigger. As T gets bigger, then this gets bigger. And as T gets bigger, then this gets bigger as well. So it seems to me that based on this equation, the number of bears is just going to keep getting bigger and bigger and bigger and bigger, which seems a bit unrealistic, really, because you'd expect there to be, on a remote island, which this did say at the beginning, especially, but even more generally, at some point the bears would run out of food. The fish population would run out, or the foods that the fish themselves rely on would run out at some point, and the bears would no longer be able to reproduce at a rate that they were before. Saying that there is no upper limit to the number of bears is very unrealistic. And similarly as well, if we were to look at the fish equation here, remember we know what A and B are, but just in the context of this question, as T gets bigger, this gets bigger. As T gets bigger, this gets bigger. As T gets bigger, this gets bigger as well. So that's also suggesting that the number of fish gets bigger and bigger and bigger, which again is unrealistic because, like I said, the fish are going to run out of food eventually as their population gets bigger and bigger and bigger. So that's why the model is unrealistic, because it suggests that the populations will increase without limit. So that's how you solve coupled differential equations, and this is the key process to remember how to do it.